Hello everyone, and welcome to today's exercise. Just 1 second. So today we are having a exercise related, as announced, related to the to a repetition of the topics of finite element method foundations. This, as I announced last week, we are doing to refresh your memory and your knowledge in the field of programming in FEPV. Because many of you mentioned that this hasn't been done so much in the last semester. So for that, maybe you saw this already, but I will also show this to you, what is prepared in the Moodle course, and maybe you have, I hope you have prepared for that already. If not, then you will need to do this now, but then of course you lose some time, but let's see. So, okay, so now you see my, Firefox, and you see our Moodle course, and I will switch it to the student view, so everything looks like you are used to it. And I want to, I will start with the material that I uploaded for you to work with FEPV. So my colleague Simon Meike, he created some videos related to FEPV, and you find them in the section tutorial videos and additional material. Those videos very nicely introduce and explain in the first video how to generally use FEP, how to start the program, what are the necessary commands that you need to execute a simulation in FEP, how to load an input file, and also how to interpret the input file, because it's you don't have a direct interface where you generate your finite element mesh and where you set your boundary conditions, but this needs to be programmed basically in a certain way in the input file. That is all shown in the first video, FEPV1. And the second video explains the structure of a user element and how this is basically carrying, or how this is involved in the FEM simulation. So both videos will be important for today's exercise, because I have prepared for you. I basically took an exercise from the last, from your FEM Foundation class. I modified it slightly. So the first task that you should do relates actually to the second video, because you are supposed to program a finite element in FEP, and therefore this FEPV2 video is related to this topic, and therefore I have here uploaded this first file, repetition FEPV. It's a 2D quadrilateral finite element with plane strain conditions, and it contains some question marks, some blanks where you should fill in the blanks basically, and everything related to this you find in, or the tasks that you need to do, and some explanation on the formulas for the formulation of the finite element you find in the first exercise sheet. I will share my screen differently so you see everything. 1 second. Okay. Okay, now you see both screens. This is not really what I wanted. Okay, so I will open the files first and then we can go through them one by one. So you should now see I am not sure whether this works. So you should now see the four-noded quadrilateral element. Can you see it? Can you maybe give me some feedback in the? Okay. Okay. Okay, now you should see it, right? Okay, perfect. So this is basically the file that is contained in the, let me check, 2D quadrilateral plane strain element file, which should be completed by you. So we will go through that briefly. Sorry for that. Okay, this way you can see it better. So if you have watched the video of Simon, then you know the basic structure of this. And if not, then I recommend you to watch it to get an understanding of what is the general structure, because it's not self-explaining. So it's a subroutine. So all of the finite elements and also the material laws that we will be programming are subroutines in the general FEEP program. So FEEP-PV is the general program, and then there's a lot of subroutines and header files to be included. So it's quite a complex program. We will not go into detail on all of these subroutines because that would simply take way too much time. What you should remember, and I will go into detail on that when we go through the exercise sheet, what you should remember is that we are only programming the computation of the stiffness matrix here for one single finite element. And then the assembly that needs to be done to combine all of the finite elements, that is done by FEEP itself. And we're not changing anything there. We're not touching it. We're not even looking at the algorithms because that would be a whole nother story. So we are basically just taking that as a black box, but we are looking at the theory of the finite element method and computing or programming basically one finite element. So you have here, or you should have in the top of your subroutine. Okay, maybe let's start with the very first line. So this is the name of the subroutine to call it. And these are the input and output variables. Some are very important to us, others we will not use. So for example, S is the stiffness matrix, P is the right-hand side, ISW is a pointer which is related to several different execution types of the element. So for example, in some cases you need to compute the right-hand side and the stiffness matrix, and in other cases you don't need to compute it. So this is kind of setting a flag for what execution is being done. I will go into detail on that briefly when we go through. And here the UL field is the displacement field, XL is the nodal coordinates. The other ones I think are explained here in the top, but they should not be of interest so much now. But remember, this is basically the variables that the subroutine exchanges with the general program. So everything that is not handed to the finite element and that is not handed back by the subroutine, the program does not know about. It stays inside here. Then we have this comment section, which explains what this finite element program is about. So it's a 4-noded quadrilateral elements, meaning we are in 2D. We have a linear elastic material model. This is what we will look into in detail in this course. I will come to that in a second. We have a small strain setup, and we have a plane strain assumption for this 2D simplification. Plane strain meaning that here we only have 2 dimensions, so saying x and y, and then the strain in z direction is assumed to be 0. This is basically the plane strain assumption. Here in the top, we have some files, some header files that are included. And these files contain the definition of several variables. For example, EL data contains data which is related to generally the elements. So, for example, N here is the number of the current element that is being executed. So let's say you would want to print out a message in only for element number 5. Then you could use this variable N and say, okay, if if N is equal to 5, then print this and that. So this N is, for example, referring to the element number. Then MA, I think, is related to the material type. So if you have 2 materials, then you have MA equal to 1 and 2 and so on. NEL is, as it says here, the number of nodes per element. So this is a more like an important variable that or that is being used in several loops here, because this indicates how many times you need to execute certain loops. Then just to pick out some files here, the IO file.h contains pointers to for input and output files. So we are writing an output file, and this is the variables to say what file, what's the file name basically that is contained here in this IO file. And this T data is maybe also of interest. So this contains all information related to the time and load steps. So TTIM is the actual time. So when we are doing a time-dependent simulation, then this variable will contain the current time. DT will contain the time step size. And to be honest, C1, C2, and so on, I haven't used this before. I would have to look it up, but this should not be of interest for us right now. Then we have the variables that we will be using defined here in this block for the initialization, and I won't go into details so much here. And here you have now the different blocks. So for example, remember I talked about this ISW. Here we have a block ISW equal to 1, and actually these ISWs are basically a translation of the command that you type in FEEP. So, for example, when FEEP is started, then the element is run with ISW equal to 1. Or, for example, if you type in the command tang, 1, then Phoebe enters this subroutine with ISW equal to 3. Or when you say plot this and that, then it enters it with ISW equal to 6, I think. So no, not 6, 8, or 4. That is the plot ISW. So this is basically what this ISW is for. It's basically a translation of the command that you type in your command window to the finite element code. It can be understood in that way. Okay, you have here, then I will maybe go and show you where the blanks are. So the blanks in your code are where the strains are computed. Then where the stresses are computed in your finite element, and also where your stiffness matrix is computed. So this needs to be filled in. And also the right-hand side, and the rest is basically given. So you don't need to, down here we have the routine for the shape functions and also for the Gauss points, for the plot routine. So this is all prepared already. So you only need to fill in the blanks. And what exactly needs to be programmed, I would like to share with you in a second, or by looking at a second file. And this is the file quadrilateral handout. This is the exercise file that you find in the Moodle course as well, exercise 1. And here, basically, the whole theory for the 2D plane strain quadrilateral element is presented. So it shows you how to, it shows you the formula how to compute the strains, and it actually derives it down to the formulas which need to be programmed. So with the loops, with the ansatz functions, the nodal variables, or the nodal degrees of freedom D. So this basically needs to be put into Phoebe, and you simply need to know what are the respective variables here. Then the same for the stresses. For the simple case, in a 1D case, Hooke's law looks like this. In a general case, it looks like this. So what you have to program is this material tensor CIJKL. Wait a second. Was that correct? What I just said. Oh, CIJKL is already given. That is the elasticity tensor, which is programmed in the variable CMAT. So that is given already. You don't need to program CIJKL. You simply need to compute the stresses based on this relation, basically. But what you need to program is the element right-hand side vector, and also the element stiffness matrix, which is here denoted by KE, but in this program given by, or in the subroutine given as S. So basically you have the formulas here that you need to type in the formulas without thinking about it. But if you think that you maybe cannot follow along the notes so well, then it makes sense to look into your finite element foundation notes once more, and we can also discuss some things here. But I hope this refreshes your memory, and you can follow a lot of what you did in the last semester already. Okay, so this is the first part of the exercise, and I will actually explain the second part when you have finished this, because I think it's a good idea for you to get started. Otherwise, I will be talking for an hour and it will get boring. Before you start with the programming, I would like to show you two more things which are not related to, well, kind of related to today's exercise. So you are seeing the Moodle course now. I have, so there's, you have probably seen there are several sections, and there is also a new quiz uploaded here for the second lecture. For the third one, there's also one coming, but this one's not prepared yet. There is two things I would like to point out in the top of the course, which is a feedback form, which I would appreciate if you fill it in. It's just very short questions on the course, and especially related to the online teaching. I would just like to get your feedback on whether you can work well with the video lectures, whether you have any problems with it, whether you put in, it's anonymous, so no name will be passed to me, but I would just like to know your opinion on the current mode of the online teaching. This is the first, so please fill this in. And also, I would be very happy if you use the quizzes. They are quite some work to set up. So if you like to work with them, then go ahead. Second thing, which is important for today's exercise, is here this sheet, this PDF file, desktop sharing in Ubuntu. So there actually is a way so that you can share your desktop with me, and I can basically take over your mouse and go through your course, or when we go to the programming and someone in the course has a question, we have the possibility to create a breakout room from this Big Blue Button session, and then we can go into this breakout room, and there you can share your screen, and I can take over your mouse, and we can look for the errors and the mistakes together. So just for that, and I will just very quickly look at the PDF together with you, if it's working. right, apologies for that. My computer crashed. I don't know whether I was going too fast with the desktop sharing. Let's hope that everything stays stable. Thanks for your patience. What I wanted to show you is the desktop sharing. So I hope my computer doesn't freeze again when I try to share this PDF with you. Okay, I think it works. So what basically you need to consider only is how to activate the desktop sharing from the student side. So what you do in your Ubuntu desktop is you click on activities, and then you type in VNC in the search box, and then these two options open, and then you click start VNC server, and what then happens is you get this terminal output, and what you would be telling me then is this IP address, and I will be using this IP address, typing it in my computer, and then there will be a remote connection between my computer and your computer. So this is all you need to do. I think it's quite easy. So in case that you have questions, we have some additional tools today to basically look at the problems in your code together. Okay, so do you have any questions right now? So the first task would be have a look at exercise sheet 1, download the element file for the subroutine element 03, and go ahead and start working on this element. Do you have questions related to this? Also, if no, then maybe you can quickly type no in the command window so I know. Okay, if you have questions, just type your name in the command, just type your name in the chat, and then I will get in contact with you, and we can discuss whatever question you have, and then I will basically leave you to work on your own. I will of course stay in the Big Blue Button room and check on you, and also after a reasonable amount of time. So I would say for the beginning now, at least half an hour, you can work on your own, and then I will check on you how quickly your programming proceeds, and then we will look at some first solutions, some intermediate solutions together, and then we will later on discuss the second exercise related to the input files together and have a look at that, and then also get into discussion on that. Okay, then have fun with the exercise. Maybe it's not so hard today because you've done this in the last semester already. Maybe you even have the solution of it somewhere prepared. Then that's good for you. Still, I think it's good to use this chance to repeat your knowledge in FEM and programming in FEEB and using FEEB as well. Okay, then I will hear and see you guys later.
Hello? Hello?
You are now unmuted. Hi. You're saying the files are not in the Fortran format, so it's not possible to download, you're saying?
I can just
Yeah, let me change the files, and I hope then you can.
copy paste it, like.
Okay, I've changed it so that you need to download the files. Maybe you can try once more. Now it should not open a pop-up window, but it should ask you to. Does it work?
Yeah.
Okay, perfect.
Thanks.
You're welcome. Thanks for the notice.
Hello, ma'am.
Yes.
Yeah, I just had a doubt regarding the shape functions derivative.
Okay.
It's a 3 by 4 matrix.
Mm-hmm.
There are 3 rows and 4 columns. 3 rows and 4 columns. Like one row is dedicated to the shape function derivative with respect to x, next with respect to y, and the last row is only shape functions, right?
Exactly. Mm-hmm.
Okay. Like it was just confusing, like why the last row was needed.
Why the last row is needed?
Yeah, like
Because in some cases you don't own like in some cases you need only the derivatives of the shape functions, but sometimes you also need the shape function itself.
okay.
And then you can call this from the third row, and then for every node.
Yeah, no. Like the matrix was shape function derivative, but the last row was this. That was confusing.
Yeah, but now it's clear?
Yeah, now it's clear. Yeah.
Okay, perfect. to get some feedback on how far you have gotten. Maybe you can quickly answer in the poll that I started, just so I know how far you have gotten. So the last thing that you finished, you should check in the poll. Okay, I see some of you have responded already. So we will divide this into two parts. In about 5 minutes, I will start and go through the programming part for the strains and the stresses. And then I will give you additional time so that you can finish the programming of the stiffness matrix and the right-hand side. Then we will switch to the second exercise. So around 5 more minutes, and then we will start with going over the first programming part.
Hello, ma'am.
Yes?
Is there any way to check our results, like after completing each small? Suppose if I written the code for strain, can I check if my code is right or wrong?
No, actually, this is not possible because you need to compile the whole element, and if you still have parts missing, you won't be able to check whether you have convergence or not. We will compare in a minute, and then you can see whether it's running or not.
Cool. Thanks, ma'am.
You're welcome. So I will go through the programming for the stresses and the strains right now. So we are starting in your code, basically for the computation of the strains. You have the formula given. Let me open that file quickly. Okay, so going to the correct position in your in this file. For the computation of the strains, we are in a small strain format. We need to program the small strain tensor epsilon, since we need it for the computation of the stresses later on. And here, this is the symmetric gradient of u, so it's 1/2 grad of u plus grad transposed of u, where with the discretization and interpolation, we have grad of u given based on the shape function. So we sum over all nodes, and then we multiply the derivative of the shape functions with respect to the global coordinates x, and multiply with the nodal degrees of freedoms d, u, I. So for the strain tensor epsilon in equation 2, you see this now written out for every entry of epsilon. And below in equation 3, you also see this given in index notation for the individual entries of the strain tensor. And since the strain tensor is symmetric, we only compute epsilon 1, 2, and then set epsilon 2, 1 equal to epsilon 1, 2. So we have to sum over the nodes in our element, which are 4. So we have a sum from 1 to 4. Then compute 1/2 times ansatz function derived with respect to x k, where k is the node, times the degree of freedom related to sorry, I should have said in which position I'm starting. So I'm starting with epsilon 1, 1. Sorry, once more. We are summing over the nodes, and we have the derivative with respect to x at node k, and we multiply with the degree of freedom at that node in direction x. So this would be d1k. And I will now share my Ubuntu desktop with you. And make this a little larger. So we are summing for k. So k is our loop counter. We are summing over all nodes. We only have one setup for our element here, so the maximum number of nodes will be 4. And now, because we do the summation, we have to remember that we always add this up to our final variable that we want to be computing. So epsilon 1, 1 is equal to epsilon 1, 1 plus whatever is added in the loop. And here in shape 1, so in the first row, we have the derivatives with respect to x, and then the column is referring to the node. So the shape function of node 1 of node k derived with respect to x would be what I marked here, so shape 1, k. And the displacements or degree of freedom at node k with respect to x would be ul1, k. So this is what you would need for the computation of epsilon 1, 1. And then based on the formula that you have given in your notes, this would be the according formula for the 2-2 entry for epsilon, where we have the ansatz function derived with respect to y and also the degree of freedom with respect to y for node k, of course. And then for the off-diagonal term epsilon 1, 2, we have this term 1 over 2 times ansatz function derived with respect to x times displacement or degree of freedom in y direction plus ansatz function derived with respect to y times degree of freedom in one direction. So this is why these indices 1, 2 and 2, 1 come up here. And then you simply, as written down in the notes, also you simply set epsilon 1, 2 to epsilon 2, 1 to epsilon 1, 2. Is this clear for everyone? How to go from how to come from the formula in the lecture notes or in the exercise notes in the description to the programming lines given here? If it's not clear, then please make notice of yourself, either unmute yourself and ask your question or just write your question in the chat. Otherwise, I will continue in a minute or so. Again, what?
Question.
Yes.
These first indices shows us the direction of the x direction or y direction or something different?
You mean the index in shape or the one in UL?
Yes.
So, okay.
Actually.
So both, okay.
Yeah.
So in shape, so I will actually, shape, to give you a complete overview. Shape comes from the call of this subroutine, shape 03, where the ansatz functions and also the derivatives are computed. And I will go to that subroutine to basically show this to you. So here you have illustrated more or less in which way we store the data in the variable shape. So shape has 3 rows and 4 columns. And in the first row, the derivatives of the ansatz functions with respect to x, with respect to the first direction are stored. In the second row, we have the derivatives with respect to the second direction, so y. And in the third row, we simply have the ansatz functions themselves. And then in the columns, you store these derivatives for their respective node. So shape 1, 1 would be ansatz function at node 1 derived with respect to x. Or shape, let's say shape 1, 4 would be ansatz function of node 4 derived with respect to x, and so on. So this is what in shape the first index is referring to. So it's not the direction of the shape functions, but it's the direction of the derivative of the shape function. And in UL, to go back to, so here in UL, also here the first index is referring to the direction for this degree of freedom. So UL actually comes, it's given to the subroutine. So it comes in a specific format, and actually you can somehow see this or interpret this from the definition of the displacement field here in the first part of the code. So it has NDF rows. So NDF is the number of degrees of freedom. In our case, we only have displacement degrees of freedom, and we are in 2D, so we only have 2 degrees of freedom, and then the star stands for the number of nodes. And here the star, this is basically a flexible way to implement this, because we are not strictly saying that we must have 4 columns or 4 nodes, but with a star it can stay flexible. So whatever is given from outside to the subroutine, the element will use it. For example, you can have a finite element like this one, which has 4 nodes, linear Ansatzfunctions, and it's just like one format. But it's also possible to write your finite element code in such a way that in the same program code you are covering linear and quadratic Ansatzfunctions, because many things are similar, and thereby you can basically save time, and also save time when programming. So your same element can execute 2 different things, and then your UL field would need to have different sizes, and this is why this is initialized with a star here. Okay, but to come back to your question, UL, so the first one is the direction, it's X and Y for 1 and 2, and K is then simply the node.
Yeah, I got it. Thank you.
Okay, you're welcome. Other questions? Okay, if that's not the case, I will go over to the programming of the stresses. And this is also, it's simply this loop that we are going to be programming. And I will go back to the exercise notes. So here in the exercise notes, it's on the second page, and as we discussed earlier, in the 1D case, sigma is simply equal to the Young's modulus times epsilon. In the multidimensional case, this gets a little more complicated, because now we have not here just the scalar, which is the Young's modulus, but we have this tensorCijkl, which you should all have heard of, the elasticity tensor or material tensor. So one option would be to evaluate this. One option would be simply to write the individual entries of sigma in a similar way that we did for the strains. So sigma 1 is equal to this times this plus this times this, and so on and so forth. For all of these entries. And actually, since sigma is a symmetric tensor, you could do it in the same way that you only compute these 3, and then the first 2, and then the 4th one, and then this one you could simply say it is equal to this one. Because of the way that these 2 operators, C and epsilon, are multiplied, you can also write this in a loop. So you see here from the index notation that sigma has the indices I and j, and C has the indices I, j, k, and l, and then epsilon has the indices k and l. So we are basically summing, remember the summation convention from Einstein. So we are summing here in this last part over indices which are the same. So we are summing over the index k, and we are summing over the index l. And in the end, by doing that, we have a 2nd order tensor, since we are doing a double contraction of a 4th order tensor C with the 2nd order tensor epsilon. If we now look at that in the code, remember what we need to program is sigma ij is equal to C ijkl times epsilon kl. you see exactly this written down here in these lines from 158 to 166. Instead of K and L, we are using A and B here. So we have to do 4 loops because we have 4 indices, and the indices A and B are for the summation for the double contraction, basically between C, which is given as C mat here, and epsilon. And you see the indices are just like we had it in the index notation. So sigma ij, and because we are doing a summation here, we have to have this part here to store, to take basically the old value from our previous loop run. So we have sigma ij is equal to sigma ij plus C ij AB times epsilon AB. So this is a very simple way of writing this out, and much more simple than writing this out in a similar way as we did for epsilon. So therefore, this would be the most efficient way of programming this multiplication, I would say. Of course, I didn't go into detail on this. Of course, we need to initialize our variables because we are doing here this summation. So we are initializing, of course, before we are computing sigma and epsilon, we are initializing the tensors equal to 0, and this can be done in this simple form here, saying epsilon is equal to 0 or sigma, and sigma is equal to 0. This could be done in also different ways. We could also in here write sigma I comma j is equal to 0. This would also work. So then whenever I start to compute sigma, I set it to 0, then I do my summation, and then I go to the next one and set it to 0, do the summation, and so either you can do it like this, you can do it like this, and there's also more ways to initialize your variable as 0. Okay, any questions related to the computation of the stresses? Let me make one remark here. In this case of the element that you are looking at right now, we are using Hooke's law, which is the most simple material model I can think of. And this is why we are simply computing the stresses right away here in this element based on the elasticity tensor multiplied with strains epsilon. In the course that we are discussing here, with the material models that we want to be considering, you remember this relation sigma and epsilon is not a linear one any longer. So this C mat is not a constant, but the C mat constantly changes because of the nonlinearity of the material response. So in that case, actually, so what we will be doing in the upcoming exercises is not program finite elements. This is left to finite elements foundations and nonlinear finite element method. But what we will do is we will compute material models, and then this part here, this computation of the stresses will be replaced by another subroutine, which is typically referred to as the material subroutine, because it computes the response of the material model. So in the upcoming exercises, we will talk about in the end quite complicated material models, which instead of Hooke's law, which could be programmed as easily as this, which instead of that can describe nonlinear material models or damage or elastoplasticity, and therefore at this position we introduce another subroutine, just as an outlook for our future exercises. Okay, maybe I will ask once more, who has finished programming? Maybe you can type your name if you have. Or no, I will do a quick poll. So you can just ask yes or no. Answer yes or no. Have you finished programming the stiffness matrix? Yeah, that is the question. Okay, so the majority says no. Then I would give you some additional time before we go over the computation of the stiffness matrix and the right-hand side. So I would say at quarter. No, maybe that's too little time. Okay, at 3:20, we will start to go over the element stiffness matrix and the right-hand side, and then we will continue with the second exercise. Are there questions? I think I asked this before, but just to make sure, are there questions related to what we discussed now? Okay, if any questions occur, if you have questions related to your own program, then just let me know and we can discuss. Okay, so then you will hear from me in about 15 minutes.
نعم يابا، عيني بالمضافة. اه روح. انا قلت لك قبل ما يطلع رن عليه خفيف. مشان؟ ما قلت لك قبل ما يطلع قول لي يا زلمه. مشان تساعد. فاهم قلت له بدي خليه يخلص محمود فيديوهاته يا خليه بس رد ارجع استنى عندي ذات الشاشة متى بلشنا؟ هاي الساعة 4 خلي كمان شوي أفرش